Welcome to the third module of the statistics portion of Math 3350 online. Today we're going to be talking about the bell curve, right? And even though the various z-tests have fallen into disuse because they've been replaced with more modern statistical tests, still the normal distribution is by far the most important distribution in all of statistics, and today we're going to learn about why. It has to do with the Central Limit Theorem, which says that sampling distributions have normally distributed means. Okay, so what's a sampling distribution? So when we draw repeated samples of the same size, they're drawn repeatedly, that's what we call a sampling distribution. For example, I could flip 20 coins and count the number of heads, and then flip 20 more coins and count the number of heads. And if I did that 100 times, I'd have a sampling distribution. So the Central Limit Theorem says that if I take the average from a sampling distribution, that the averages will be normally distributed. And the interesting part is not just for normal populations, but for any distribution, any crazy ski jump shaped distribution, bimodal, doesn't matter what the shape of the underlying population is. If the number of trials is large enough, the resulting distribution of the means will be bell-shaped. And not only that, the important thing of the central limit theorem is it tells us exactly what the mean and the standard deviation will be. So this notation is important. We use it throughout this course. So the capital N indicates a normal distribution. And then the first slot specifies the mean, and the second slot specifies the standard deviation. Okay, so what are we saying here? We're saying that the underlying distribution, the probability density function for the underlying distribution, if it has a known mu, these sampling means are going to have the same mean. They're going to be clustered around the same mean. And the standard deviation of the sampling means, the sampling distribution means, are going to be the sampling distribution standard deviation divided by the square root of n. So the normal distribution will have a standard deviation that's related to, but not exactly the same as, the standard deviation from the sampling distribution. But the cool thing is it will have the identical mean that the sampling distribution did. And of course, this square root of n in the denominator is important because we want to think about what happens as n gets large. So as n gets large, we're talking about the law of large numbers. And the accuracy of these estimates. So what do I mean by these estimates? Well, generally speaking, in statistics, we have a numeric data set and we calculate the sample standard deviation x bar. But the idea is to use that to estimate the population parameter. Yeah, we know, let's say, the average for 200 students at the University of North Georgia, but we don't know the average for 18 to 22-year-olds nationwide, right? The population parameter mu might be the value for all college-age students nationwide. X bar is the sample of data that we collect, but the idea is to use the sample mean to estimate the population mean. And the law of large numbers says those estimates become much more precise as the sample size increases, which makes sense because of this square root of n term in the denominator. The standard deviation is going to 0 as n goes to infinity. So the law of large numbers says that our estimates get better as our sample size increases. Let's talk about the standard deviation. It's obviously critical to the central limit theorem and the law of large numbers and how they work. And we haven't spent much time trying to understand what the standard deviation means. It can be used as a distance metric in a data set, but the question is why? So you see these formulas, but let's go ahead and work through a 3-column proof. So what I've done is I've copied the data set over here to the tablet, and I'm going to take you through the 3-column proof. The first thing we do, the first column is just the data set itself. And to calculate the mean, to calculate the standard deviation, we need to know the mean. So we are going to take the sum of all the values of x, and we have 9 plus 1 is 10, plus 6 is 16. So our average is 16 divided by the number of elements in the data set. So our average is 4. Our second column is going to be our deviation column. And so we're going to take each individual x and we're going to subtract the average, right? So this will be a deviation. So the deviation for 1 is 1 minus 4 and negative 3. So notice this deviation is negative, meaning that this x is to the left. On a number line, it's to the left of the average. And the same with 2. 2 minus 4 will be negative 2. So negative 2 is also to the left of the average. Now what about 4? 4 minus 4 is 0. When we have 0 deviation, then the data point is sitting on the average, right? It doesn't deviate at all. And now here we have a data point that's to the right of the average, and we have a positive 5. So we'd like to think of an average deviation. That's what the standard deviation would accomplish. The difficulty is, if I add up all these numbers, I get 0, because the deviation tracks whether it's to the left or the right using this minus sign, so the sum of the total deviations is always 0. So while it's a nice check step to make sure that we're on the right track with our deviations and have calculated them properly, it doesn't help us with the idea of average deviation. So we're going to need to apply an operation that gets rid of the negative signs, but preserves the relative magnitude. Larger numbers will still be larger. So we've got two options. We can use the absolute value and we can use the standard, the square of these deviation numbers. And by the way, there are standard deviation metrics built on both. But the traditional one is built on squared deviations. So we're just going to take the middle column values and we're going to square them. All right, so negative 3 squared is positive 9, negative 2 squared is 4, 0 squared is still 0, and 5 squared is 25. And we're going to add these up and we're going to get 38. Okay, so now this is better. Now we have a list of numbers that we can add up and we get something different than 0. But we have two problems. The first problem is, think about the units. If the units over here were dollars, deviations would still be dollars, but as soon as I square it, now I have dollars squared. So our units are wacky. So we'd like to take the square root. And then we have a second problem we're trying to correct for. If you think about what we have currently, just adding more data points would make the standard deviation bigger. So we want to scale this 38 number by the number of data points, right? So let's do that first. Let's divide 38 by the number of elements in the set to get 9.5. And this is the 9.5 is the average squared deviation. The average squared deviation. And now if we take the square root, we'll have the standard deviation. So the square root of 9.5 is approximately, maybe I should use approximately equal to 3.08. All right, so that's our standard deviation. 9.5 was our variance. and the square root of that is our standard deviation 3.08. And we use sigma and mu for the population mean and standard deviation. So what we have here is we've just calculated this, right? We sum up the difference, these deviations, we square them, we sum them up, we divide by the number of elements in that data set, and then to get sigma, we take the square root, okay? Now the sample standard deviation is almost exactly the same, except that we divide by n-1. Now, it's beyond the scope of this course to talk about biased and unbiased estimators, but it turns out that especially for small sample sizes, this standard deviation actually underestimates. It's a biased estimator, and it turns out to be too small. So when we calculate the sample standard deviation, we will get a different number. As a matter of fact, the sample standard deviation here is about 3.5. So I've pulled out my graphing calculator here and I entered the data set, and now I can go to Stat button, Calculate menu, get the 1var stats, and you can see that the calculator is listing 2 standard deviations, and it's listing the standard deviation with an S for the sample standard deviation. That's the 3.559, right? The one that we calculated is sigma, which was approximately 3.08. So that's what the difference is. There are 2 different calculations. Why do we have 2 different ones? Again, the population standard deviation turns out to be biased. So in actual practice, where we're running t-tests, where we're running ANOVAs, where we have maybe only 30 observations, 25, 10 observations, we're in these small sample sizes where the sample standard deviation is a much better estimator of the actual standard deviation. And because it's this average squared deviation value, it can measure a typical or average distance in a data set. That's why we can use it to check for outliers. That's why in small data sets we say any data point more than 2 standard deviations away from the mean can be considered an outlier, right? Because a standard deviation is a typical distance, and if you're more than 2 standard deviations away from the mean, you're kind of exceptional. We'll talk about the Central Limit Theorem at the end, and you'll understand the percentages a little more in just a moment, but that's the key idea. We're covering a lot of ground. The next topic today is normal curve calculations. So the reason the bell curve is so useful is because each vertical line in the bell curve corresponds to an exact percentile, which means that if we know the raw score somebody has in the distribution, we can figure out their percentile. And if we know their percentile, we can figure out what their raw score was. So the whole idea of standardized scores comes from this standard deviation, right? And so we can do it by hand using a table. But most often, if we don't have R open, we'll use a graphing calculator. And we can trick the z-test into behaving like an interactive table for us. RStudio has an even better option called XPnorm. So the RStudio version is just pnorm, and then XPnorm is like extras. It's like the pnorm normal probability calculator that'll calculate these p-values with some extras, and that's the one we're going to use. And we can do the reverse process on the TI calculator with inverse norm, and in RStudio with XQnorm. So pnorm and qnorm are the 2 formulas that we want to take a look at. So let's just talk about 2 typical distributions. SAT mathematics. So components of the SAT, this isn't perfect because tests are different, years are different, but they have approximately, their average is approximately 500 with a standard deviation of 100. And so like on the SAT math, where the maximum is 800, right? The maximum is about 3 standard deviations above average. And IQ tests were designed to have an average of 100 and a standard deviation of 15. Like they're set up in that way. So Maria's SAT math score was 630. What is her percentile rank? Okay, so when we are given a raw score and we're asked for a percentile or a probability, right, we're going to use z-test. So if you go to Stat button, Test menu, see this very first option here is z-test, and we're going to sort of trick the calculator. I'll show you how in just a second. So for mu sub 0, that's the population value. We're going to put in a 500 and 100. So for the first two values, the mu and the sigma, those are the population values, and I'm getting them from right here. Now, x bar. Well, x bar means the sample average, right? But for x bar, we're just going to use 630. Sorry, let me get this 630. Okay, and what's the trick? Here's the trick. I have a one-person group. When I set n equal to 1 on my graphing calculator, you remember that square root of n in the denominator? That's square root of n is going to be square root of 1, so there won't be a denominator. It will just calculate this z-score for me. But it makes sense, right? X bar, we're just trying to calculate Maria's percentile. So Maria is a group of 1. So when I set n equal to 1, the calculator is set up how we need it. P-values are percentile ranks are the percentage of people who scored lower. So I'm going to use the less than inequality. And then I'm going to hit draw. And it shades, it does several things that are helpful. It creates this vertical line at Maria's score. It calculates the z-score, the standardized score, and it gives me the exact percentile. Okay, so now we know that Maria's percentile is 90th percentile. And by the way, if this were 0.9099, it would still be 90th percentile. We don't round percentiles, we truncate. Now I've switched over to RStudio, and all I did was I did File, New Notebook, and then I selected all the stuff that comes up in the template and deleted it. So then we hit Insert, some R code, and I'm going to type in XP norm, and I put Maria's 630 raw score first, then the mean, and then the standard deviation. And when I hit play, a couple of things happen. First of all, I get the nice interactive chart. It calculates the z-score, it draws the vertical line, and it shows me what area is where. Also, in the console, it shows me that it shows in terms of probabilities, the probability of being in this distribution and being above this vertical line is about 0.9032, just like our graphing calculator. Excuse me, that's the area to the left, and then the area to the right is 0.0968. So this gives me all the same information, and it's slightly better. Okay, so what about knowing somebody's percentile and wanting to go to their IQ? I'm sorry, I switched on the wrong thing there. So we're going to use the graphing calculator. And this is a little different. We're going to second vars. The vars key right here has distributions. And so there are several different really helpful functions here. We're going to use option number 3, inverse norm. And we're going to go inverse norm of 0.7. So this is an important thing to note. Whenever that you're putting a probability or a percentile or a proportion into the graphing calculator, it's expecting it in decimal form. So this is not going in as 70, it's going in as 0.7. The comma is above the 7 key, so 0.7, and then tell it the mean and the standard deviation. So 500, comma, 100, close parentheses. And then when I hit enter, I find that, oh wait, I did the wrong mean and standard deviation. This was asking about IQ, and I did SAT. So let's put in 100 for the average IQ, and then 15 for the standard deviation of the IQ distribution. And so if she's 70th percentile, she's about 107, 108. And in R, we can do the same thing. We can come up here and insert some R code, a chunk, a code block. We're going to do XQ norm. And we are going to see it brings up the little tooltip here and tells us we're looking for the probability first, and then the mean, and then the standard deviation. So our probability was 0.7, and then 100, and then 15, and then we can hit play. Right? It will tell us this value, right, where it draws the vertical line, and it shows us that it's doing 70% to the left and 30% to the right. And when I look at the graph, it has calculated the standardized score for me, right? And if I want to know the raw score, I come back over here. And so this matches up with what we found on our graphing calculator. So either way is fine. To finish this off, let's do a couple. What do we do when we want to find the area between two values, right? So when they originally, I don't want to get too serious about IQs. People get too upset about intelligence and what it means. And I just like using it because all of these politically incorrect words like moron and imbecile and idiot, when they originally created the IQ distribution, those words were actually ranges on the original IQ scale. If you look up, although Wikipedia is getting more and more politically correct, but you can still look up some of the original IQ scales and see them labeled in terms of moron, imbecile, idiot. So just as a lighthearted look at IQ, and not trying to be, it's a little politically incorrect, but let's just have some fun. They actually were just calling people dullards, right? And they said if you had an IQ between 51 and 75, then you're a moron. Okay, so if we have this distribution, what percentage of people in a distribution like this would have values between 50 and 75? Well, if we do this on the graphing calculator, what we have to do is run the z-test twice, right? So we'd set up the z-test for, and by the way, there are two input modes. We're going to use stats input mode for this one rather than data input mode. We'll use data input mode later for hypothesis testing, but stats input mode lets us put in the mean and the standard deviation. For the IQ distribution, that's 100. For the mean, 15 for the standard deviation. We can put in an IQ of, what were we looking at? 75 was the top end there. So I'll evaluate. It's just a little easier to see. So 75, just one person at an IQ of 75 with the less than inequality. And when we draw that, you'll see it's going to shade just a little bit down here. Draws the vertical line at a standardized score of -1 2/3, and the p-value is just less than 5%, right? So about 5% of the world have IQs less than 75. Okay, so in R, we can accomplish the same thing a little bit faster. So let me just go back up here where we have the XP norm. What I'm doing now is I'm using this concatenate function. So if you know anything about computer programming, concatenate just means to shove two things together. So now what we want to do with XP norm is we want to give it both the left-hand endpoint of the interval we're looking at and the right-hand endpoint of the interval we're looking at. And it will do both calculations at once. When we're using the graphing calculator, yeah, we have the right-hand endpoint, but this left-hand endpoint over here, we're going to have to use the calculator a second time. We have to write down this information, use the calculator a second time, and then subtract the p-values. And that's fine if you have a graphing calculator. That's a good way to go. But R is going to do this all in one go. Why? Because we are giving it two inputs where the raw scores go using the concatenate function. And when I hit play, you'll see that it's doing two areas, right? And giving me the probabilities relating to, it's doing two vertical lines and it's giving me the probabilities relating to two different ones. So this purple, you can barely see the purple over here, right? There's just a tiny bit of purple, and you should run this on your own in your own R notebook and you'll see it. So there is something down there, and they're giving us the probability that you're even below purple, and they're giving us the probability that you're between the two. This is the value that we want. Okay. The probability that your IQ is between 51 and 75. All right, so it appears that approximately 4.72% of the world are morons. When you're at Walmart after midnight, it seems like that number should probably be higher, right? Okay. And then just to flip this around, find the middle 90% of the math distribution. This is related to statistical estimation. We often want to find the middle portion of a normal distribution. And on the graphing calculator, of course, we can use inverse norm. So let's show that. Again, we go to second vars. Option 3 is inverse norm. And if I just put in 0.05 without any mean or standard deviation, it will calculate the standard normal value it'll calculate the z-score corresponding to the 5th percentile. Okay, if I do inverse norm and I can put in the distribution, it'll recalculate that for the raw score. So for SAT math, we had a 500 average, a 100 standard deviation, and so you see that about a 335, 336, which of course is probably going to be a 340 because the SAT only gets scores in increments of 10. That would be the 5th percentile. And then we do the same exact thing except for the 95th percentile, right, is 664. This creates a symmetric interval, and there is 5% below, right? So we have this bell-shaped curve. Sorry, that's not great. And we've drawn these two vertical lines, and since we use 0.05 as the p-value, we have 5% of the area down here, and we have 5% of the area under the curve over here, which leaves 90% in the middle. So now we have we know that 335 and 665 create a symmetric interval with almost exactly 90% of the area in the middle. So the final thing I want to talk about is the empirical rule. And this is helpful to know because this is the structure that all bell curves operate on, and this is what makes them really useful. So what we know is that in any reasonably symmetric bell-shaped distribution, that 68% of the data points are going to fall within 1 standard deviation of the mean. So these light blue or teal lines here represent this is 1 standard deviation above and 1 standard deviation below mean. And in between there, you're going to find 68% of the data, right? The next stage is 2 standard deviations between -2 standard deviations and +2 standard deviations. And there you're going to get 95% of all the data points. This is why in a small sample, we can use the 2 standard deviation away from the mean rule to identify outliers. Right? If you think about it, if you have a sample of 20 objects, you're going to expect about one of them to be further away from the mean. So this is not an appropriate way to check for outliers in a large data set of 100 or 200 or 1,000. data points, but in small samples, say 50 or less, it's reasonable to check to see if data points are more than two standard deviations away from the mean and call those outliers. And now we have the 3 standard deviations away from the mean, and if I go out to 3 standard deviations below to 3 standard deviations above, I capture 99.7 of all the data. So that's the empirical rule. And one way to think of this when you get graded on the curve, and that doesn't happen much. What happens most times now is what I call the gift. Points just get added to people's scores. When professors and high school teachers say they're grading on the curve, they usually mean they're grading on the gift. The actual curve says that, all right, we are going to call this range here B's. Anybody who's above average but less than 1 standard deviation above average is going to get a B. Anybody who's below the average but not more than 1 standard deviation below the average will get a C. Then the D and F range is everybody who's more than 1 standard deviation below average. And then the A's are only going to be those who are more than 1 standard deviation above average. And I'm old enough that I was graded on the curve. We took a class, this is going to date me, I took a class called Intro to the Soviet Union, and it was a current affairs class, not a history class. And there were about 800, the 800 students in the class because the professor was an award-winning, very entertaining and passionate scholar, taught the course, and so he taught it once a year, and they filled up a big lecture hall with students, and it was very engaging. But they gave 50 question multiple choice tests, and 90% was probably a C. You know, you'd be lucky if getting a 90%, if getting 40 out of the 50 questions, multiple choice questions correct was actually an A. It actually took something like 45 out of 50 would be 90%. But if you only got 45, you were in danger of a C. It'd probably be a low B. And you had to get 47 or 48 out of 50 correct to be in the A range. Why? Well, they just calculated whatever the average was and whatever the standard deviation was, and they assigned the grades so that about 2/3 of the class got B's and C's, about 1/6 of the class got A's, and about 1/6 of the class got D's and F's. Okay, so that's what it means to grade on the curve, but it's also a good way to kind of understand what we mean by 1 standard deviation above. Yeah, you're doing great. That's the A range, but you know, this BC range is what's typical, right? You're supposed to, if you're doing average work in the class, this is, you know, B is slightly above average, but still very average. B and C is slightly below average, but still very average. So that's an explanation of the empirical rule and why it's important. People used to use the empirical rule to calculate or estimate these probabilities we did on the prior slide. But it's still important to know and kind of understand this is why it was, this structure of the bell curve is always true. And it's that underlying idea that makes these normal distributions so helpful to us. So there are a lot of great simulations in the document. So we're talking about these underlying distributions, and we end up spending a lot of time here illustrating these. We do random trials and coin flips and showing the central limit theorem and the law of large numbers in action. Here we only do 50 trials, but then we do 200 trials, and you can see the bell shapes emerging. So definitely go through the dynamic course notes in our studio, use this document, and then create your own notebook and practice with these different things. After we get done with the central limit theorem and discussing it, we also show how to do these normal curve calculations. So definitely take some time with this and try to make our studio do these calculations as well. In post-production, I realized that I hadn't done a good job of explaining what the z-score was. I had just been talking about it. So let me go back and say that standardized scores, that's the connection between a raw score and its exact percentile. And I mentioned this a little bit in a prior video, but let's make it explicit. So when we're talking about a standardized score, we start with some raw score. For example, if your IQ is 110 and you're in some normal distribution like the IQ distribution, or we talked about the SAT distribution or ACT distribution earlier in this video. So you take a raw score. You take your raw score and you take a deviation, right? You just subtract the mean from your raw score, and then you divide by the standard deviation. So what does the z-score tell us? The z-score tells us the number of standard deviations above or below the average that the raw score is. So let's just say you had a z-score of 1.5. Because it's positive, it means you're above average, and this means you're 1.5 standard deviations above average. If it were negative, if your z-score was negative 1.5, that means you would be 1.5 standard deviations below the mean. So this is what I had mentioned in an earlier video. In the old days, we used tables because everything was calculated in terms of the standard normal, and then all the lookup could be done in a z-table. So you could convert the negative 1.5 or whatever your z-score was into an exact percentile. And you could go the opposite direction to convert a percentile back to a z-score. But again, this is the connection between the raw scores and the percentiles, is this standardized score. Sorry for leaving it out. Hopefully this helps tie the information together.